Understanding Physics, and this video is about AP7, Assessed Practical 7, which is about simple harmonic motion. So what we're going to do is we're going to use a pendulum to find a value for little g, acceleration due to gravity, and we're going to use a mass on a spring. We're going to find the stiffness of this spring in two different ways. So these are the tasks that I usually get my students to do, which will satisfy the criteria, hopefully. So first of all, pendulum. You need a retort stand. You need your pendulum, which is a light, inextensible string. So just a piece of cotton, in other words. For the bob, I have some metal balls, like heavy ball bearings with little loops on them that you can tie the string on. But really anything like a sphere, some kind of a ball would do. As long as you're measuring, when you're measuring the length of the string, you're measuring to the middle of the bob, the center of mass of the bob. Okay, a G-clamp to stop the retort stand from wobbling, because that would be a systematic error. I mean, what you could do is just tie the string to something rigid, something solid, and then don't use a G-clamp, whatever. But the standard way of doing it is a G-clamp and a retort stand. A meter ruler to measure the length, a digital timer, some kind of a stop clock to measure the period, and that's your equipment. So now for small amplitude oscillations, in other words, just a couple of centimeters, small oscillations. Why? Because if you've got this bob swinging like crazy, the angles are big, and when we derive the equation, t is 2 pi root L over G, we assume small angles. There's a small angle approximation. So basically the equation doesn't work for large amplitudes. So small, just a couple of centimeters amplitude, horizontal amplitude. And you measure the time it takes to do 10 oscillations, and you divide that by 10 to get the period. And you do that for at least 7 different lengths. I would suggest from 30 to 100 centimeters, 10 centimeter intervals. I wouldn't do less than 30 centimeters, because then the time gets smaller and smaller, and of course the percentage uncertainty will get bigger, won't it? A fiducial marker. Now, a fiducial marker marks the middle, the center of the oscillation, and that's where you're supposed to time it from. So it's like you start the watch when it goes past the fiducial marker, and then you stop it when it comes back in the same direction past the fiducial marker. It's supposedly a more accurate way of doing it. Make sure you mention it in your report. It's a way that you are doing it to make it more accurate. Then you plot a graph of t squared against L. So the period squared against L. And as t equals 2 pi root L over G, okay, if we square both sides and say y equals mx, then the gradient of this graph will be 4 pi squared over G. So get the gradient, 1 over the gradient, multiply by 4 pi squared, and it usually gives a pretty good answer. So you've got a value of G using a pendulum. The mass on the spring, the equipment, so you'll need a spring. Your teacher will give you a suitable spring to use, some 100-gram masses up to, about 800 grams. Okay, I wouldn't go more than 800 grams, because then you might permanently deform the spring. You don't want to do that. Again, G-clamp the retort stand to the bench, or use a rigid support. Sometimes I turn a lab chair upside down, and you can just hang it off the lab chair, and that's really rigid. And a timer. So I said we're going to get K 2 different ways. The first way is just put 800 grams on it and measure the extension. Yeah. measure the original length, measure the length with 800 grams on, the difference between them is the extension, and just use K equals F over X to find the stiffness. I mean, you could do it for different masses up to 800 grams, and then just to make sure that it's a straight line, so you haven't gone past the limit of proportionality. But basically, an experiment you should have done in maybe year 7, yeah, to get the stiff, or at least year 9, to get the stiffness of the spring. Now, method 2, if you put 300 grams on the spring, pull it down a couple of centimeters, again, small amplitude, then let go, and it will bounce up and down, and you can time how long it takes to do 10 oscillations, divide by 10 to get the period. Do it for 300 grams to 800 grams. Less than 300 grams, you try it, it's not very stable, and it bounces up and down quite quickly. So a minimum of 300 grams. Again, more than 800 grams, you're in danger of going past the limit of proportionality. So 300 to 800. Again, some kind of a fiducial marker to mark the center of the oscillation. I mean, whether you can be bothered doing that or not, but at least mention it in your report. Okay. And so you're varying the mass and you're measuring the period. And we do a graph of t squared against m. And as t equals 2 pi root m over k, square both sides, y equals mx. So here my gradient will be 4 pi squared over k. So get the gradient, 1 over the gradient, times by 4 pi squared, and that's the stiffness of the spring. And you can compare your method 1 and your method 2. These are the bits and pieces which you're supposed to be ticking off, and weirdly this H and I don't know why they've put this there, because we're not going to do it using a signal generator and oscilloscope. We're going to do that later on, so don't worry about that. You know, generate and measure using waves, blah blah. Very, very strange they put them in there, because this won't satisfy them. You know, A, B, C, no problem. H and I, no, don't worry about it. We'll tick them off later.